Section 6 is called free body diagrams. We're finally going to learn one of the most valuable types of drawings that we can make in physics, known as the free body diagram. So when we're solving dynamics problems, it's going to be incredibly useful for us to assemble all the information that we have about the forces that act on the object or the body into a single diagram called the free body diagram. This represents the object as a particle, no matter what the object is. It could be a particle, but it could also be a ball, it could be a body, a person, it could be just a block or a truck or a train or whatever. You're just going to represent it as a particle, a dot, and show all the forces that are acting on that object in a very simple way. So the steps for drawing your free body diagram are here. Identify all the forces that are acting on the object, of course. We've been doing that sort of thing all year long. Then draw a coordinate system and use the axes defined in your pictorial representation, whether they are tilted or not, to help you with your free body diagram. Represent the object as a dot at the origin of the coordinate axes. So you're actually going to draw your axes on your free body diagram. This is your particle model now. Then draw the vectors representing each of the identified forces that you have, and you want to label each of those vectors. So if you have a thrust vector, T. If you have, you're going to have F sub thrust. If you have a tension vector, T. If you have a friction vector, F sub lowercase f sub s or lowercase f sub k, and so on, okay? Then, let me scroll up here. Then, draw and label the net force vector. If you have a known net force, then draw that vector beside the diagram. This is kind of important here. It is going to not be on the free body diagram itself. It's going to be off to the side, okay? And you're going to label that F net. And check that F net points in the same direction as the acceleration vector in your motion diagram. Okay, so if you have a motion diagram drawn, or if you know what the motion is, then the F net should be drawn in the same direction as the acceleration. Or if you don't have a net force, then off to the side, you're going to write F net equals 0. Okay, that's going to be important. That's very important information if you don't have a net force. So we're just going to practice a little bit with free body diagrams. So this first practice problem says an elevator suspended by a cable speeds up as it moves upward from the ground floor. So draw a free body diagram of the elevator, and we're going to want to include all of the information that they just told us in this problem, and there actually was a lot of information there. So we have practiced a little bit with drawing like a pictorial representation of what's going on. So let's start with that. What am I going to draw?
Elevator.
A very simple elevator suspended by a cable, just like they said, okay? So I have a cable, and then I have an elevator. It's just going to look like a box. That's it, okay? I don't even need to draw any people inside it. So there's my elevator. Now what do I do?
Circle it.
Why do I circle it?
No, you want a ground floor, right?
Nope, I want to circle it. Is this elevator on the ground floor?
No.
No, it's not. It's going up. It speeds up as it leaves the ground floor, okay? So I circle just the object in question, and then notice that the circle that I made cut through the cable. So that means we have a contact force because of the cable, okay? That would be a tension force, that's right. So now we're going to go off to the side, and we're going to make our free body diagram. And so, are we going to have regular axes, or we're going to have tilted axes is the next question.
Axes?
These are just regular axes. So we're going to draw those on there. So here's my y-axis, here's my x-axis. So x, y, totally straight, as we can tell. And now my free body is going to be this dot right here in the center. Okay? That's my elevator. It's now a particle. It doesn't matter. This is my free body. The axes are centered on my particle. Okay? It's a free body. That means it is floating in space or it's on the ground, it doesn't make any difference anymore. It's free to be wherever it is. Okay? Now, we need to start identifying vectors that are forces being applied to this object.
Tension.
So we have a tension vector. Which way is it pointing? Up. Okay, now this tension vector up will be called what? Okay, so we label it T. Any other vectors that are forces applying?
Great.
Yes, there is a weight vector. Because the elevator has mass, it will have a weight to it pointed down. Now, because this elevator is speeding up, we want to represent the fact that it is speeding up, and that means we will draw the weight vector how? Down.
Less.
It will be shorter than the tension vector, okay? So, I draw my weight vector down, but it must be shorter than the tension vector, obviously shorter, so that we can have an acceleration up, okay? So that will be called what? W. And I should be putting vector symbols over the top of these forces. Okay. Any other forces going on here?
Let's see here. No normal force, no thrust force, spring force. No. Okay, well, would there be drag in this case?
No. No drag because this is an object that is not moving super fast.
Very large object, not moving very fast.
Right.
Oh.
Okay, but is there any other force that I need to put on this drawing?
Not thrust.
Not thrust. That is, the motion is taken care of by the tension in the cable. Go back to the instructions that we have.
There wouldn't be friction, right?
Not that we're talking about. There you go. F-net. Is there an F-net here?
We're not getting one now.
We're not told that there is, but are we speeding up? Which way are we speeding up? We're speeding up. And that means we have an acceleration up, which means the F-net must be in the same direction as that acceleration. So off to the side, I will write F-net. Okay, it is a vector, so it's a vector symbol above the F-net. And I got to draw an arrow in that direction, up. Now we have completed the free body diagram. All right, so let's go on. Can I go on? Okay, here we go. Draw a visual overview. So the visual overview is composed of a motion diagram, a force identification picture, and a free body diagram for a car as it accelerates from rest. Okay, so the motion diagram. Do you remember what a motion diagram looks like?
Yeah,
Yes, the dots and the...
Dots and
The
arrows. What type of arrows are we drawing?
acceleration.
No, it's velocity. Yeah, velocity vectors. Okay, so this car is accelerating from rest. So how will these arrows, or how will these dots look? They start out close and then they're getting farther apart. Okay, so let's draw that. So I have a dot and then another dot that's kind of close, and then the next dot is a little farther apart, and the next dot is farther apart, and then much farther apart. Okay, so that's pretty good there. So then we would have vectors in between. Longer arrow, longer arrow, longer arrow. And you said that these are what? These are velocity vectors.
We need to label it.
Yep. And then this would indicate that we have an acceleration going on as well. In what direction? So my acceleration vector would be in the same direction as the velocity in order for us to be speeding up.
So isn't that putting in a force identification? No.
Nope, this is just the motion diagram.
So how come?
Okay. The next thing we got to do is the force identification picture. So this is where you draw the actual situation and then you draw the circle around the situation so you can identify the forces. So what am I actually going to draw here? I'm actually going to draw a car. Yeah, it's going to be an amazing picture. So the car is going to be on the ground. I'm going to have, obviously, a two-wheeled car, happily moving along. And it looks like this clearly, yeah, and there's got to be a window. And it's going to have a smiley face in the front because it's a happy car.
It's a happy car?
Yep. And it's going to have, motion lines out the back.
My car would have 10 out of 30.
This is a pretty good looking car. Okay, so now what do we do?
Circle it.
I circle the car.
And then draw that.
No, we need to identify the forces. This is a force identification picture. So we cut through some things here.
You got weight?
Okay, so we have a weight vector down.
We have a normal force vector up at the same,
Because we're on the ground and we have a weight vector down, we're going to have a normal vector up.
at the same length, right?
As far as we know, it would be the same length, yes. Because if it's not, either we're going into the ground or we're floating away.
Don't we have kinetic energy?
We don't know anything about kinetic energy right now.
Wait,
Kinetic friction?
yeah, I'm sorry.
Okay, so which way would the kinetic friction be pointing in my drawing?
Away, or
That's
opposite.
Opposite the direction of motion, right? And my motion lines are showing that I'm moving to the right.
So it's gonna point.
So the kinetic friction would be F sub K to the left. Good. What else do we have?
Let's see here, drag,
Nope.
no tension, no thrust.
The thrust.
Oh,
We
thrust?
could call it thrust. It's a force, right?
Because it's from rest, when you accelerate.
We are, yeah, so we are accelerating to the right, so we must have some sort of force going to the right, correct?
Yeah.
Okay, so we could call it thrust. I don't know what else we would call it. So we have some sort of force pushing the car along. I drew this line here. How should I draw that line? Should it be longer than?
Longer,
Definitely.
Why longer?
because you're accelerating, so that means.
That means it has to counteract the force of friction, right? So we could call this F sub thrust. It kind of looks like I drew a rocket exhaust there. Maybe it is a rocket car, I don't know.
Mark's definitely not.
F sub thrust is the name of thrust. Okay, any other forces?
Oh, wait, we have to do.
That's it. Okay. So now our next move is to draw the actual free body diagram. So
Oh, this is where we do the.
now we draw the coordinate axes, yes. We're
You
not
don't have to tilt it again.
we're not tilted. We're drawing along level ground. So our x-axis positive will be to the right, which makes sense because we're moving to the right. Positive y will be up. We have a free body diagram now, so the car is now represented by a dot.
So you're gonna have a longer arrow to the right,
Okay.
so at thrust.
Our thrust, ooh, what's going on? Going slow, okay. Our thrust vector is to the right, F sub thrust.
And a smaller vector to the left, the
Okay, F sub K.
and then you're gonna have two equal going up and down.
Yes, the weight vector down is supposed to balance with the normal vector up. So those are meant to be drawn the same length.
Now,
Now
is
we
there
do
any-
that.
Okay, F net, off to the side.
Pointing to the right.
It would be pointing to the right because we are accelerating to the right. So F net to the right.
so is there gonna be a case where, like the equal force is gonna be stronger than the weight?
The normal force, you mean?
Yeah, normal force.
So if we have a tilted axis, we're going up a hill, down a hill, something like that, the weight vector would be split into components, and the normal force would still be perpendicular to the hill that we're on. Okay? So then the component of weight that is perpendicular to the hill would match the normal force. We'll do problems where they're like that. Okay? All right, so that's it. That's how you do those. Okay, so now we have the popular tow rope pulling a skier up our snow-covered hill at a constant speed. Draw a full visual overview again of the skier. So this is, once again, the motion diagram, the force identification picture, and then the free body diagram. So what does the motion diagram look like for this
It should
situation?
be constant velocity, right?
Constant velocity, the tow rope is going to pull at a constant speed. So remember though, we're going up a hill, so
Yeah, go for that.
tilted axis on this one, but we're not drawing axes, we're just drawing the motion diagram right now. So the dots, my dot might start here, and then all the dots will be spaced equally apart because we're going at a constant speed. Then I gotta draw arrows between, and all the arrows will be equally the same length. I gotta label this velocity. And now, do I have an acceleration? I do not. Acceleration equals 0. That's an equal sign.
Then when we did the
That's right, you're thinking ahead, and yeah, the F net is going to be 0. Okay, now I gotta draw my, what? Gotta actually draw the skier. This is the force identification picture next. So we have our hill. Wow, that's a super steep hill. We have our skier. Notice I never use a snowboarder because snowboarding is terrible. And then we have, let's see, that's legs, we have the body, we have the head, we have the arms desperately holding on for life on the rope.
You gotta make them sad.
We have, oh, definitely sad. And then the hat. Poles would be dangling off to the side, dragging along the pain and suffering of going up the rope tow. All right, what's next?
circle. Wait, I said circle.
Well, I said it first.
All right,
Oh, we got kinetic
Friction.
friction.
Yeah.
okay.
Energy friction.
Kinetic friction going which way?
Down.
It goes down?
The hill.
Down the hill, okay. So kinetic F sub K. All right, what's next?
Wait,
Tension.
Weight vector goes which way?
vertically down there.
Directly down towards the center of the earth. Weight vector. Okay, what else do we have? Tension. Directly along the rope,
Yeah.
we have tension. We have a normal force perpendicular slope, that's right. So I will try to put it here. I shouldn't have drawn my picture the way that it did, but here we are. So here's our normal force.
We all got
Anything else?
No.
No? Okay. So next is what?
Free body diagram.
Free body diagram. How should I draw this?
Tilted.
Tilted axes. So my x-axis will be tilted along the same line as the hill. And this will be my positive x here. My y-axis needs to always be perpendicular to my x-axis. Positive y will still be up according to the hill. My skier becomes my free body in the middle at the origin of the axes.
So you got weight from the
Okay, weight comes directly down from the particle. That's my weight vector.
Is the weight of normal force the same?
No, the weight and normal force will not be the same length in this case. But if we were to break the weight vector into components, we would have a W sub Y and a W sub X. Like this. And the W sub Y and the normal would be equal. Okay? So that's when we start solving problems later on. Okay, what else do we have?
You got normal force going on the y-axis, right?
Normal force going along the y-axis. So normal, okay,
And then you got going directly on the x-axis.
okay, F sub K, F sub k
And your tension is going to be the one that's
is tension going to be longer?
yes, this is pulling it
Okay, but not for the reason you think. Tension. The reason that tension is going to be longer, actually, I might as well point this out now because of what I did earlier, is because we have a weight vector pulling us down the hill and a friction vector pulling us down the hill, and those two vectors add, and that's why the tension vector is going to be longer than the other vectors. Because we have a net force of what? The net force has to be 0 because we have no acceleration. We're going up the hill at a constant speed.
But tension is a stronger force than
Tension has to be stronger only because we have a weight vector pulling us down and a friction force resisting us from going up. Okay? And those two down vectors add. So tension has to overcome both of them to give us a net force of 0 so that we have no acceleration. And that is why the tension force is actually longer than the F sub k. Okay? Does that make sense?
yeah.
That's a little ahead of what we wanted to do with this one, but it's perfect that we talked about it now because now you hopefully would understand that when we get to having to know that. All right, any other questions? Okay, so we're almost done. An elevator is suspended by a cable and it's moving upward and slowing to a stop. Which free body diagram is correct? We'll take a second to think about it and then come back and answer it. Okay, so let's analyze each one of these answers here. A is showing that the tension is greater than the weight. If that's the case, what would the elevator be doing? It would be speeding up because the acceleration would be in the direction of the net force, which is up. In B, it looks like the tension is the same as the weight. In that case, what would be happening?
The elevator would be moving at a constant velocity.
Constant speed, yep. In C, looks like the tension is shorter than the weight. In that case, what would be happening?
It is slowing down.
We'd have to be slowing down, or we'd have an acceleration in the down direction, but we're moving in the up direction, which means we're slowing down. In D, I'm not even sure what this is, okay? But those two vectors would add, so I would take this vector here and I would add it to the top of this vector, which means we have a longer vector here than this one, which means we're speeding up. And F net equals 0, what does that mean? There's no acceleration, which means we're going the same speed. So the only possible answer for this situation is C. All right, so that's the whole section. We're done.
Yeah.